But it's working.
Okay, next talk is by Bastian Brandt on QCD at finite isospin chemical potential.
Yeah, first of all, let me take the opportunity for thanking the organizers for organizing this very nice conference and for giving me the opportunity to speak here. So I will be speaking about the phase diagram of QCD at finite isospin chemical potential, and this is recent work done together with Dirac, and he actually got his ME Newton group for that, so that was the reason why we could recently in Frankfurt. Well, it's not just a nice thing to look at because it shares some similarities in problems with QCD at finite baryon chemical potential, but it's also a very interesting system to look at because it has a rich, somehow a rich phase diagram, and you can look at several things in this phase diagram and investigate things that go even beyond the phase diagram in the QCD with finite isospin chemical potential. And even more, it appears natural in the phase diagram of full QCD because there are a lot of physical systems where we have an isospin asymmetry in the system, so that's important to include also the isospin chemical potential when we consider QCD at finite chemical potential. I would like to start with an introduction into the topic, a very short one, before I talk about our simulation setup and introduce these in famous lambda extrapolations. Then I will come to the physics result, where we look at the phase transition to this pion condensation phase. And then I will be talking about the small isospin region, where we're looking at the crossover when we turn on the isospin chemical potential. And then I will say a few words about the comparison of our results to Taylor expansions. All right, so we're looking at QCD at finite chemical potential. Let's start just with the NF equals 2 case. There we have a U and a D for chemical potential, and the physical effects, or the chemical potentials that are relevant for the physical effects, are the baryon chemical potential and the isospin chemical potential, which is basically the difference between the two. And a non-zero value of this isospin chemical potential basically introduces an asymmetry between isospin plus and minus 1 particles. And such situations where you have this asymmetry, as I said already, occur regularly in nature, for example, within nuclei, when you have more neutrons than protons, but also within neutron stars, and presumably also in the early universe. Usually, of course, the effect of finite isospin chemical potential is much less pronounced than the one due to finite baryon chemical potential. Nonetheless, we will here consider the baryon chemical potential to be 0 because in that case we are not having a sample. Okay, so how can we include the finite isospin chemical potential in our theory? We are just adding this term here to the Dirac operator, which is proportional to this Pauli matrix, the third Pauli matrix, which has a 1 and a minus 1 on the diagonal. And when we introduce this term, then this breaks the vector SU2 symmetry explicitly down to this residual U tau 3 1 symmetry here. When we then crank up the isospin chemical potential, then this residual symmetry will be broken spontaneously by the presence of a charged pion condensate at some point, and you can basically view this U tau 3 symmetry as creating rotation in this plane of charged pion operators. And when we have this charged pion condensate here, then this singles out a point, and then we will develop one Goldstone mode, which is basically going along this direction here. At t equals 0, we know where this will happen. This will happen at the isospin chemical potential at m pi half in our definition of the isospin chemical potential. So the expected phase diagram has been mapped out by Son and Stefanov using effective field theory. So what they found was, of course, this pion condensation phase here, and then just due to the symmetry breaking pattern here, they expect the phase boundary to be second order in the O2 universality class. And they also conjectured that there should be some first order deconfinement transition line here coming from the fact that when you crank up the isospin chemical potential and send it to infinity, you should basically arrive at pure gauge theory, and they thought that somehow this deconfinement line here should be originating from this pure gauge theory here and continue. There are basically just two lattice simulations on the matter, and they are on very coarse lattices. The first one was here by Kogat and Sinclair. They used NF equals 2 and later also NF equals 3 at pion masses bigger than the physical one. And they basically found that this first order line and this pion condensation phase boundary could actually join. That was what they saw. So they said that there might be the existence of a tricritical point, which is basically just this endpoint on the phase boundary here. Another simulation by the four Cohen collaborators has used NF equals 8, also at pion masses bigger than the physical one. but they tuned it such that the transition here is first order, and then they were trying to see whether it weakens or not when they crank up the isospin chemical potential. And what they actually found is that the transition indeed becomes weaker, and that would then speak against the existence of a tricritical point. So all of this phase diagram has basically not been mapped out by the lattice so far, and this is what we are trying to do in the setup with physical pion masses. All right, so let me now come to the simulation setup. So we are having 2+1 quark flavors. We have a strange quark which has no chemical potential and is a standard rooted staggered fermion. And we have mass degenerate UD quarks, and the fermion matrix looks like this. So we have the standard staggered Dirac operator with Stauchschmidt links in this case. And we have these off-diagonal elements here. And what this does, so these off-diagonal elements are basically introducing a small explicit breaking of the residual symmetry. And this is necessary to observe the spontaneous symmetry breaking in a finite volume. And it also serves as a regulator in the pion condensation phase, where we have this Goldstone mode, meaning that we are accumulating near or exact zero modes in the case of infinite volume, of course. Okay, so our quark masses here are tuned to their physical values, and these are our lattice sizes. We have also now already lattices at n tau equals 12, but here I will mostly focus on this lattice size because that was basically the starting point for our analysis. And but we now want to obtain physical results from our simulations. What we need to do is we need to remove this parameter lambda. You basically send it to 0. However, the problem is that the dependence on lambda for most of the quantities is not really known. So what I show you here is the lambda dependence of the isospin density, and you can see that it's very difficult to find a curve which would, in particular a polynomial curve, which would describe all of these points. And the same is true when you look at the renormalized chiral condensate. So it's really very difficult to tell what this lambda extrapolation actually looks like. In addition, we want to remain model independent. I mean, that's the reason why we're actually doing lattice simulations, because we don't want to introduce any model dependence. So the best thing that we can do is to use somehow a cubic spline extrapolation that basically means that we are using a spline fit, where we fix one of the outer points to be the point where we want to extrapolate to. Then we try to get the value at this point, so the function value at this point. There is one thing we need to assume here. So we actually need to stabilize the extrapolation a bit. What we need to assume is that the last 2 points that we have are actually lying on one part, cubic part of this curve. There's of course another remaining systematic fact, and that is concerns the node points of the spline that we are using, and they will influence the final result. So what we actually should do is we should average over all splines that give us a similarly good description of the data. So what we can do here is we can perform a spline Monte Carlo, where we allow for changes of the number of node points and also the node position, and then weight all the splines according to some suitable action, which represents the goodness of the fit in some sense. There are two possibilities for these actions. We can use the archaic information criterion, that would give us an action like this, or we can also use the negative goodness of the fit, which results in an action like this. And we have actually checked that the results that we get do not really depend on the particular action that we choose here. There is one more problem. You can obtain oscillating solutions even though the data is basically flat. So it could still be that the spline somehow wiggles, hits the data but wiggles, and this is something that of course you don't want. So you can somehow get rid of that by including some measure, which I call here delta for these oscillations, and basically just including that in your action, which would then suppress these solutions. So I will not talk about how we choose this delta here. However, our final action then for the spline Monte Carlo somehow looks like this, where we have one free parameter here, and that needs to be tuned. If f is too large, then that means that basically this term delta suppresses all of the curvature, and this is of course not what we want, right? So we want to allow for curvature in the fit. So f needs to be tuned such that you are in a region where your result does not really depend on the value of f, but you are still far from the region where it suppresses every curvature in your fit. And when we use the archaic information criterion as an action, then and for our choice of delta, of course, then we found that f equals 10 is a rather good choice. And here I just show you the resulting extrapolations that we get from the spline, and that's again for the isospin density. You can see that it does what it's supposed to do. So if we have a basically flat extrapolation, it is also giving us a flat line here, and the error bar is rather small when the lambda equals 0 line here. When we have some more curvature, it's capturing that, and the error is getting a bit bigger. And if we have really a rather steep extrapolation, then of course the error bar here is getting bigger, because what determines this extrapolation are basically the last 3 points here, so there is less information in the data that we have. So it really does what it's supposed to do. Okay, so let me now come to our physics results, and let me go directly to this pion condensation phase and its boundary. So the onset of the pion condensation phase is signaled by obtaining a non-zero pion condensate, which is defined in this way. And I will from now on use this renormalized version. I will not talk about renormalization here though. And the problem for this quantity directly is that here the lambda extrapolation is particularly steep. Okay, this is really the most problematic quantity concerning these lambda extrapolations. That might also have to do with the fact that it's actually the derivative with respect to lambda of the energy, basically. All right. So in addition, the transition point itself, so the onset of the pion condensation phase, is defined by the point where it leaves the value of 0. And to really determine this point with high accuracy, that really demands high accuracy in your lambda extrapolation. So it's really hard. So we actually need another formalism for this quantity here. So what we can do is rewrite the pion condensate in this way, and then use the singular values that are defined in this way here to rewrite the pion condensate basically in terms of the density of the singular values at 0. And this is really the analog to the Banks-Kesher relation for the chirocondensate that you know, I guess. And this relation has first been derived in this paper here. And this is something that we can do. So what I show you here is the density of singular values. These are basically the lowest 100 singular values that we could compute. And so you see that here the pion condensate will still be 0. Here there's some of the onset of leaving the value of 0, and then here you get a clear non-zero value for the pion condensate. You can even do one more step. You can perform a leading order reweighting of the pion condensate. So you rewrite it in this way, where this W is basically just the ratio of the Fermi determinant with at finite lambda and at 0 lambda. And then you can expand that in lambda, and to leading order, this ratio is given in this form here, and then you can include that. And what you get are then these 3 points here, and you can see that the resulting lambda extrapolation is very, very flat, so you can do it with high accuracy. And compared to this standard lambda extrapolation that you would get if you just naively compute the pion condensate at every value of lambda and then extrapolate it. Okay, so this combination really allows us to accurately extract the phase boundary. So this is an example how then this this final result for the pion condensate looks like for different values of lambda. So you see that there is clearly the point where it leaves the value of 0, and we can extract that, and this is the pion condensation phase boundary you get. So it really looks a bit voxel-like, but there is some curvature here in this region, and then it turns to flatten out. All right, so that of course is just at one lattice spacing, so we include other values of nt, and now I'm going up until nt equals 12. You can see that there's not so much of cutoff effects here, but in this region, well, we see something, but I mean that is basically mostly lying on top of each other, and okay, here we still don't know, so that's still something to do. Okay, so let me now come to the region of small isospin chemical potential. And here we are mostly interested in the behavior of the crossover temperatures when we switch on μi, and we are interested in the region where we are below the pion condensation phase. Of course, we define Tc by the behavior of the chirocondensate. Usually one could, for example, use the inflection point. However, here we choose an easy alternative. We just use the point where the subtracted condensate reaches a certain value, and we can do that because here we are still in the silver blaze region. All right, so that's what we do, and this is our definition for the condensate, and this is the same definition that the Budapest-Wuppertal collaboration has used, so we can basically just take their value that they found at Tc and use that as our definition for the crossover temperature. So let's see how that works. So this is now the renormalized chirocondensate versus the temperature, and this is the point which it should hit, where we define our value of the crossover temperature. You can see that it agrees quite well at μi equals 0 with basically the turning point of the condensate here. Now let's include point at finite values of μi, and you see that not much has changed when we go to a low value of μi. So basically Tc has not changed at all, and the same remains true when I include another value, so a higher value of the isospin chemical potential. However, then suddenly something appears to have happened. Okay, so that's rather strange. Why should there be such a big jump? However, well, it's still the question about these lambda extrapolations. This should still make you aware of the point that these lambda extrapolations are really the thing that you need to control here. Because when you look at the lambda extrapolation of these 2 points here, you see that they are basically not very reliable. So we need to work much harder to get these points reliable. So this, in particular, this temperature here for the crossover cannot be used. Okay, so really the main thing to control here are these lambda extrapolations. All right, so now I have 3 crossover temperatures here. And I can just include them in my phase diagram. That are these 3 points here. And you can first of all see that the temperature here is lower than the shoulder of this pion condensation phase. And the other thing you can see is that the curvature of this crossover line here is very, very mild. So there's basically no curvature, mostly no curvature here in the region. All right. So there are, of course, a lot of open questions that we would like to answer. So first of all, where is the meeting point between crossover and the pion condensation boundary? What is the order of the transition on the boundary? Is there a tri-critical point there? What happens in the limit when we really crank up mu(i) and send it to infinity? And more generally, are the deconfinement transition and the boundary of the pion condensation phase equivalent? So these are all questions that we would like to answer in the future, but we are certainly not there yet. Okay, so let me now talk in my last few minutes about the comparison of our data to Taylor expansions around mu(i) equals 0. And I don't think that I need to introduce the concept of Taylor expansion. The problem, however, with Taylor expansion is that the range of applicability at a given order is unknown a priori. Okay? So what we can do here is we can really test the Taylor expansion method using our data at finite values of mu(i). And as an observable here, we choose the isospin density, which is defined in this way. And the associated Taylor expansion basically looks like this, where we have 2 coefficients here. And once more, we can take the values for these coefficients from the Budapest-Wuppertal collaboration. And I will now show you the comparison for 2 different temperatures. One is below Tc, so it's this temperature here. And when we then crank up the isospin chemical potential, then we at some point hit this pion condensation phase boundary. And from that point on, of course, we do not really expect any agreement with Taylor expansion, because, I mean, the state of matter has changed from here to here. And then I will use another temperature, which is up here. And in that case, we will not hit this pion condensation phase, at least not for the values of mu(i) that we have at the moment. So there we can really test the agreement with Taylor expansion, up to which order it agrees. All right, so let me first start with the temperature which is smaller than Tc. And these are our results for the isospin density, and this is the result from Taylor expansion. This curve here is order mu(i), and this curve here is order mu(i) cubed. And you can basically see that, okay, I mean, below the point where we hit the pion condensation phase, which is approximately here, we cannot really distinguish between the 2 curves with our data. And from that point on, it really deviates from the Taylor expansion curves, and that's as expected, basically. Okay, so let's now get to T being bigger than Tc. And here we can see that while up to this point it's still very difficult to distinguish between the 2 curves, but then somehow the order mu(i) cubed correction is becoming significant, and our data really follows this order mu(i) cubed curve here. But there's also no room up to now for an order mu(i) to the power of 5 correction. So it would really be interesting to see whether this remains true when we actually include higher values of the isospin chemical potential here. Okay, so this is one thing that we would like to do. There is one more obstacle here. Actually, we are comparing to coefficients from a 6 times 18 cubed lattice. However, we've explicitly checked that finite size effects for these coefficients are negligible, and we can also check it with our data because we have other lattices. And I can just do it for an 8 times 24 cubed lattice, and you can see that basically the same conclusion holds. And when I go to T bigger than Tc, that's basically the same what we had before. Okay, so here the coefficients are really computed on the same lattice size. All right, so as I said, so it would still be interesting to simulate at larger values of mu(i) for T bigger than Tc to really see how long this agreement with the order mu(i) cubed curve persists and when order mu(i) to the power of 5 corrections are setting in. Okay, so that already brings me to the summary and perspectives. So we have here investigated the phase structure of QCD at finite isospin chemical potential. The biggest issue as I've told you, are really these lambda extrapolations, and they have full control. That's really important. And for some of our points, that really still needs to be improved, as I showed you. Right? So we have mapped out the transition to the pion condensation phase using the pion condensate, and this new lambda extrapolation method helps a lot in really identifying that. We have also investigated the crossover temperatures and found basically almost no curvature at all. It's a very mild dependence on μi. And we have compared our results to Taylor expansion, and they agree well to the order of μi cubed. There is really a lot of things to do here. We are just starting to look at this at the QCD final isospin chemical potential. And so in particular, we want to perform a continuum limit. We also want to determine the order of the transition, as already said. And there are plenty of other interesting things you can look at. And this is what we're planning to do in the future. So stay tuned for new results on that. So thank you for your attention.
Thank you for the nice talk. Questions?
Just a couple of comments about the lambda extrapolation. One is that let's ignore for the moment your reweighting. The type of extrapolation using the eigenvalues is equivalent to doing a valence form extrapolation. And the other thing is that usually if you deal with susceptibilities, you can actually get a far better idea where the critical point is than you do from the condensate itself.
And that is true. That's certainly something we want to look at.
And if you get any idea as to what the nature of the transition is, then the right extrapolation, of course, at the critical point is according to the critical index associated with that type of transition. So you probably should also deal with, not only deal with susceptibility, but also deal with things like fourth order bin accumulants, because they give you an idea as to what the universality class is for the transition.
Yeah, that's exactly what we plan to do. However, for that you also need high accuracy. So I mean, we still need to work on that. I mean, the number of configurations that we have at the moment is not really sufficient to really compute the bin accumulants. But that's something we would like to do in the future.
Thank you.
Other questions? Yeah.
There have been works by Furthershot and Heller on how to introduce, how to do random matrix theory at finite isospin chemical potential. So all you have to do is compare your low-lying eigenvalues of the Dirac operator with that of the random matrix theory at finite isospin chemical potential and compare them to get the pion condensate. And you can actually do away with your lambda extrapolation. This is all done at lambda equals 0.
Yeah, thanks a lot. That's a very good comment. So something to do. Yes.
Can I ask one?
Yeah.
How did you renormalize Carlo condensate?
Carlo condensate, well, let's switch back to that slide. So we multiply it by the mass, and then we use the t equals 0 subtraction. Let me check what is it. It's here.
No more questions. Thank Bastian again.